We will continue on the topic of chromatography. So, as I mentioned, the peak that is coming out of a column will appear like a normal distribution or a Gaussian distribution, and you have the width at the base, and then this is called the half width at half the maximum. Okay, this is the width at half the maximum. So, these parameters are used quite a lot for doing some calculations, which we will see that later. So, if you assume a Gaussian distribution, then the concentration as a function of time will appear like this. It will be C0 exponent T by T naught minus 1 divided by 2 sigma square. T naught is called the retention time, C naught is the maximum concentration the solute will appear, okay, and T naught sigma is the standard deviation. You can compare this equation with the normal Gaussian function, as you can see, x minus b whole square divided by 2c square. Okay. So, that is how it looks, that is how it is analogous. So, we can also have corresponding to T and T naught, we can also have V and V naught, where V naught is the volume required to be eluted out of the chromatographic column for it to reach the maximum concentration. Okay. So, here V naught sigma will be the standard deviation, whereas in the other case it is T naught sigma as a standard deviation. So, how do you get that? You get that based on comparing the traditional Gaussian function. These equations are very useful, as you can see later on we will use it for many calculations. So, the total amount of the solute that is coming out of the column is, if I integrate that equation from 0 to infinity. But if I collect samples between T dash and T only, then the amount of the solute that is eluting out will be integral of C into Q dt. C is the concentration, Q is the flow rate, this is the time between the two limits of T dash and T. Whereas, if I am going to collect from 0 to infinity, then the same equation will appear with two different limits, 0 to infinity. So, okay. So, obviously, the yield of I will be this divided by this. So, if I am collecting the sample between T dash and T, so I am ignoring whatever is coming out before T dash and I am ignoring whatever is coming after T. So, some material will be lost. So, the yield will be this divided by the bottom equation, and that is what it is, as you can see. And then we can the amount eluted out will be the given by this, okay, because C is given by this relationship as I showed before. Okay. So, we can substitute in that and you come up with a new function that is called ERF. ERF is called error function. Okay, I will define that more in detail later on, but this is called error function. So, yield is given by half of error function of T by T naught minus 1 divided by square root of 2 into sigma minus error function T dash by T naught minus 1 divided by square root of 2 sigma. Okay. Here you are collecting samples between T dash and T. Okay. Similarly, if we want to use V, then instead of T we put it as V. So, we get V by V naught and V dash by V naught. Now, what is this error function? The error function is defined like this: error of x is equal to square root of 2 by pi integral 0 to x e minus u square du. Okay. So, you can, there is a table available for different values, okay, of x, what is the corresponding error of x. Okay. There is a table available which we can use it, I will show you that. So, if T and T dash are equal, okay, then there is no yield. Okay. That means T and T dash are equal. If T dash is equal to 0, the error function term containing T dash will be equal to minus 1. Okay. So, you will end up with half of 1 plus error function T by T naught minus 1 by square root of 2 sigma. Okay. So, if you are collecting the sample from time equal to 0 right up to time, okay, then you will get a equation of this form. Okay. So, when you are collecting from time equal to 0, okay, this term will go away, actually this term will go away, that will be minus 1. So, you will get half of 1 plus this term actually. So, you are collecting sample from time equal to 0 up to time equal to t. So, you will end up with the equation of this form. So, if there are many solutes like I, J, K and so on, many solutes, then of course purity of solute I will be C naught of I into yield divided by summation of C naught of J into yield. Okay. So, this could be many solutes available. So, you will have, if there are 3 solutes, you will have 3 terms at the denominator, that is the purity, it is obvious, right. So, let me define what is error function. Error function, as I said, for different values of x, there is a table available which tells you what is the error of x. Okay. So, when error x is 0.00, that means if you are integrating between 0 and 0, then error function will be 0. Okay. If you are integrating between 0 and 1, you end up with the error of x as 0.842, because you have 2 by square root of pi. So, when it goes to 3.4 and above, 3.41 and so on, okay, because then you will get error function as 1. So, basically error function graph looks like this. So, this is a change in x and this is the y axis gives you the error of x. So, it is almost going up and then reaching an asymptotic value above 3.4 onwards. This is how error function looks like actually. This is also known as probability integral, this is also known as Gauss error function and so on actually. So, this table is very important if I want to calculate, for example, yield if I am collecting samples from 0 time to time t. Okay, I use this equation. So, I will calculate all these terms and error of x, whatever is this, then I go to the table and pick up my corresponding value and substitute there, that is how it works. Okay. Now, I want to introduce some new terminology, theoretical plates. I introduced this terminology in the previous class. A chromatographic column can be expressed in terms of theoretical plates, which gives a quantitative measure of its efficiency or separating power. How did these theoretical plates come? It came from chemical engineering. So, if you look at the original distillation column in chemical engineering, distillation is used for separating liquids with different boiling points or liquids which have different vapor pressures, right. So, originally the distillation columns, tall columns, they had trays inside or plates inside. So, the vapor will flow upwards and the liquid will flow downwards. So, it will come from one tray to down, another tray to down, another tray and so on, and at each tray there is a vapor liquid contact, equilibrium, mixing and all takes place. Okay. So, more number of trays you had, more efficient was the distillation column in separating two liquids. Okay. So, more number of trays, it can separate out two liquids with closer boiling point. That is how it happened. So, they believed that when you have many plates, you will have better distillation efficiency. When they moved into packed column, that means you had a packing inside, you did not have trays inside. If they want to compare this with the original tray distillation column or plate distillation column, they wanted to have some relationship of converting the packing height to number of trays, so that it becomes easy for one to compare. Okay. So, there some equations were developed which related the packing height to number of trays. So, same thing is used in chromatography also, because you have a packing in the as a stationary phase. So, can I call a certain length of the stationary phase packing equivalent to certain number of trays? Then it becomes easy for you to compare different chromatographic columns. We can say this column A has 100 plates and column B has 110 plates. Then column B is more efficient than column A, because it has got more number of theoretical plates. So, that is how the concept of theoretical plates were extended from distillation column which had plates or trays to packed distillation column and then to chromatographic columns as well. Okay. So, the efficiency of the chromatography process is measured by the number of theoretical plates. It is not measured by the column length, but because column length alone is not enough to tell the efficiency, there are the type of packing, so many other factors come into in deciding the efficiency. So, if I can convert this into n, the number of theoretical plates, then it is easy for one to compare two different columns and we can also say whether this column is good or not very good and so on. So, the number of theoretical plates for a chromatographic column can be estimated by this formula, equal to 16 divided by TR, that is the retention time, divided by the width at the base of the peak square. Okay. If we assume it as a Gaussian distribution, then the number of theoretical plates is also given by 5.54 multiplied by TR, that is the retention time, divided by the width at half peak height square. So, we can use this formula or this formula. If I know the width at the base, I can use this. If I know the width at half peak height, I can use this formula. Okay. So, if I have two, all I have to do is I inject a sample into my column chromatography, and then see when the retention gets coming eluted out, that is the retention time, and I determine the width at half the height or width at the base of the peak, and then I use one of these formula to calculate n. So, I can if I have two columns, I can do the same injection of the solute in both the columns, and I can estimate from the TR and WB or W half the number of theoretical plates. So, I can say this column is more efficient, that is this column has more number of theoretical plates than the other. Okay. This is how the theoretical plate concept was extended to chromatography as well. There is something called resolution. A resolution is a measure of how two chromatographic peaks are separated. Are they good or are they bad? Basically, resolution is determined like this: 2 into the retention time for peak 2 minus retention time for peak 1 divided by width of base 1 peak 1 plus width at base for the peak 2, or we can say delta t, that is the difference in the retention time divided by W average, or if it is if you are measuring the width at half the height, then it will be 0.589 delta t by W average. Okay. So, the resolution depends on column selectivity, separation factor, retention factor, capacity factor, and number of theoretical plates and so on actually. Okay. So, resolution, this is how it looks like. These peaks are very well resolved. Okay. So, you can have, this is almost at a distance of 6 sigma, resolution may come out to be 1.5. So, resolution 1 means they are just touching each other at the base, and as the resolution keeps going down, they start slowly overlapping. So, when poor resolution almost 0.5, we can see large overlap between these two peaks. Okay. So, the higher the resolution, farther away are the two peaks. Okay. Resolution between peaks improves with the length of the column, but the problem is if you increase the length, the elution time also increases. The selectivity can be modified by modifying the composition of the mobile phase, changing the column temperature, changing the stationary phase, using some chemicals and so on actually. There is something called peak asymmetry, because although we say Gaussian peak and so on, but peaks are never Gaussian. You may have a tailing, that is slowly it is decaying, or it is called, this is called a fronting. So, both are possible actually. So, the tailing factor is defined by A plus B divided by 2A. What is A? The front portion of this is called A, and the back portion is called B. Okay. So, the tailing factor TF is A plus B divided by 2A. Generally, this factor will vary between 0.9 to 1.1. You will never get exactly 1, but it will vary between 0.9 to 1.1. Okay. So, you can have some tailing or some fronting. Okay. A is an indication of the fronting, B is indication of tailing. So, if you have that, then we can get an equation for the number of theoretical plates, 41.7 TR divided by W 0.1. Okay. It is not W half or W base, it is 0.1. That means the width at 10% of the height, okay, divided by A by B plus 1.25. Okay. So, there are different ways by which one can calculate the number of theoretical plates using width at the base or width at the 10% of the height or width at half the height and so on. So, there is something called plate height. So, if you have a number of plates, then if you have plate height, if you multiply it together, that will give you an idea of the length of the packed portion. So, plate height can be minimized by reducing particle dia. Okay. Smaller the particle, better is the separating efficiency. Reducing column dia, changing column temperature, reducing thickness of the liquid film that is forming on the packing, optimizing the flow rate of the mobile phase. So, all these can reduce the plate height. I said thickness of the liquid film, so that depends on the physical properties of the continuous phase like viscosity, density, surface tension, dielectric constants, interaction with the matrix and so on actually. So, all these are issues which can affect the plate height. The columns designed for high flow rates at higher than atmospheric pressure, these columns are stainless steel or high density glass or acrylic components. This is how the chromatographic columns are made actually. You all know about HPLC, that is the high pressure liquid chromatography, high performance liquid chromatography. Generally they are used for analytical purposes, they are not generally used for separations in industrial scale, okay, because they are very small diameter. So, sample injection is very limited in this actually. So, what are the detectors? The HPLC detectors could be refractive index detector, ultraviolet fluorescent detectors, radiochemical, electrochemical, near infrared, mass spectrometer, nuclear magnetic resonance, light scattering. So, large number of detectors can be used. We will not spend time on those because we have shortage of time. Similarly, if detectors for gas chromatography, we can have flame ionization detector, nitrogen phosphorus detector, electron capture detector, thermal conductivity detector, flame photometric detector, photoionization detector, electrolytic conductivity detector, mass spectrometer and so on. So, large number of detectors depending upon the type of compounds you are separating, whether it is ionizable, not ionizable, whether it is UV visible, all those things actually. Okay. There is something called thin layer chromatography. This is you do it on a piece of glass plate which is coated with silica. So, it is very cheap, minimal sample cleanup, wide choice of mobile phases, flexible, easy sample detection, high sample loading, ease of handling. This is widely used in chemistry synthetic labs for a very very long time. It can be used for small molecules, it can be used for larger biopolymers as well actually. So, basically what you do, you have a glass plate, you coat it with the silica and then you put an initial mixture of your the mixture, and then you have a solvent here, it could be a mixture of solvent. As time progresses, the spots keep moving up. As you know, silica is extremely hydrophilic, so it does not move, whereas hydrophobic material will start moving. So, as time progresses and progresses, you are going to have many spots. Depending upon your optimization of the mixture of solvents, you will get clean and beautiful spots. So, the top could be hydrophobic and the bottom most is the most hydrophilic. This is a very good technique and that is called TLC or thin layer chromatography. Alumina is the strongest adsorbent, followed by charcoal and so on. Silica gel is the least absorbing in the group. Okay. Alumina as the adsorbent, then you use different solvents for these solute mixture to travel upwards, right. So, you can have petroleum ether and they have the least eluting power, and then we have cyclohexane, carbon tetrachloride, benzene, dichloromethane, chloroform, ether, ethyl acetate, acetone, ethanol, methanol, water and pyridine. So, if alumina is the adsorbent, least eluting power solvents are given in that order. If alumina is the adsorbent, the greatest eluting power are organic acid. Most strongly adsorbed are acids and bases and amines, while least strongly adsorbed are saturated hydrocarbons, alkyl halides, unsaturated hydrocarbons. So, they will travel much faster in that order, you know. Saturated hydrocarbons are extremely hydrophobic, right. So, they will travel faster and reach the top first, and so on as you come down to ethers, esters, aldehydes, ketones and finally alcohols. The relationship between the distance travelled by the solvent and the solute after they have reached the equilibrium is expressed as RF value, that is the distance travelled by the solute divided by the distance travelled by the solvent front. Okay. So, that is called the RF value. So, each component will have different RF values and that is very characteristic of that component. Now, let us look at something called ion exchange chromatography. Okay. So, basically if you have an ionic mixture like you have positive and negative. Okay. So, we have a packed column which has either positive ions anchored on the support or it could be negative ions, and sometimes you can have mixtures also. So, what happens when you pass an ionic mixture? Okay. So, the negative ions will get captured on the ions which are anchored. So, the positive ions will flow nicely. Okay. So, later on I can use a buffer to elute out these negative ions. So, where do you use this? We can use the, suppose I have a protein and salt solution, I want to remove the salt because salts are charged. So, I can use an ion exchange chromatography. There I can use both cationic and anionic anchored to the support. So, the sodium chloride can get captured and my protein can move down. That is the advantage of ion exchange chromatography. So, we can have both ions present anchored to the support, cationic and anionic both together. So, how do you then recover? We can pass a buffer, okay, so that they get removed, or we can change the pH of the solution so that the whatever salts are captured can be removed. This is ion exchange chromatography. It separates biomolecules based on the charge, stationary phase, ligands of certain charge. So, it is all based on charge. Biomolecules is the mixture of opposite charge will attach to it, whereas with the same charge it will pass through, obviously, right. So, we can have cation and anion. So, immunoglobulin G and bovine serum albumin are separated on a strong anion exchanger using a linear salt gradient. Okay. So, bind enzymes, proteins and ions of interest and allow contaminants to pass through. Okay. So, that is later on bind the charge contaminants, other approach, bind the charge contaminants and allow the molecules of interest to pass through. Depending upon the concentration of the impurity, we can do both. If the impurity concentration is very little, we can try to capture them and allow your product to pass through, and vice versa actually. For an anion exchange, functional groups used are aminoethyl and quaternary ammonium, whereas for cation exchange, functional groups used are carboxymethyl, sulfopropyl and methyl sulfonate. Okay. Sulfonic and quaternary ammonium groups form strong, while other groups form weak ion exchanges. So, variation of ionization as a function of pH determines the strength of the ion exchanger system. So, when I change the pH, obviously the ionization change. So, that strength also change. Okay. The binding also changes actually. So, these are ion exchange media, like I will have a cellulose or agarose. Okay. Then I can have a diethyl aminoethyl. So, you will get a lot of positive charge, or quaternary ammonia ethyl, or if I want to have a negative carboxymethyl group. So, this has a negative charge, or sulfopropyl group which also has a negative charge. Okay. So, cation exchangers will have carboxymethyl, as you can see carboxymethyl, cation exchange, or orthophosphate, sulfonate, sulfoethyl, sulfopropyl and so on. So, these are the functional groups there. Okay. Here it gives you see the pK values also here, very acidic. Okay. Now, let us look at the anion exchange. We have diethyl ammonoethyl. Okay. So, it will have plus, all these will have trimethyl hydroxypropyl, quaternary ammonioethyl, triethyl aminoethyl. So, pK values will be in the basic region 9, 9.5, polyethylene amine and so on actually. Okay. So, these are anion exchange, whereas cation exchange, as I said, is carboxymethyl or sulfonate, sulfoethyl, sulfopropyl and so on actually. The capacity of ion exchange chromatography depends on pH, ionic strength of the buffer, nature of the counter ion, flow rate of the solvent, temperature. For example, increasing flow rate decreases the dynamic capacity of the system, obvious, right, because the residence time decreases. So, how do you elute out? We can have very different techniques for eluting out. We can have isocratic elution, that means concentration, salt of certain concentration, stepwise elution. I will change the concentration from one value to another. Gradient elution, continuously changing the pH or ionic strength. Affinity elution, I can have a affinity ligand passing through which will capture whatever has been bound. Displacement chromatography, that means I can displace whatever has been done using some other solvent or some other material. So, this is how you regenerate your column. You have to regenerate after each cycle. You can use a salt solution until the ionic strength reaches about 2 molar. The salt solution should contain the counter ion to the ion exchanger, so that there is a equilibration taking place. There could be denatured proteins or lipids which may remain in the column even after regenerating. Okay. So, we need to wash it then with sodium hydroxide solution, so that the contaminants get removed actually. So, it is quite strong sodium hydroxide, because some denatured proteins or lipids may be still stuck. Okay. And sometimes if there are microbes present, we need to sanitize. Of course, the sodium hydroxide also helps in the sanitization. Next one is hydrophobic interaction chromatography. We looked at ion exchange. So, in this hydrophobic interaction, we are separating proteins based on their hydrophobic nature of the surface. So, I will have matrices which are hydrophobic. Okay. So, what will happen? Proteins which are hydrophobic will get bound and proteins which are hydrophilic will get flushed out. Okay. Then I can have a change in the salt concentration, or I can use a detergent or a solvent. So, whatever has been bound, the hydrophobic ones can be collected. Okay. So, this is how the hydrophobic interaction chromatography works. So, basically it is separation based on the differences in the hydrophobic nature of the proteins. Okay. Basis of difference in the hydrophobic interaction, all proteins will have hydrophobic groups. There could be hydrophobic amino acids. Okay. Basically those with non-polar group R groups like alanine, phenylalanine, valine, tryptophan, leucine, isoleucine, methionine, phenyl groups, hydrocarbon chains, all these contribute to hydrophobic nature, and depending upon how much of these are exposed, the hydrophobicity of a protein varies. If they are buried inside, then it will look more hydrophilic. Okay. So, all these groups contribute to the hydrophobic nature of the protein surface. So, the process involves loading a protein mixture suspended in a high salt solution. Why are you doing high salt? So that there is some sort of a salting out, okay. Eluting the proteins by decreasing the salt in the solution, or changing the polarity of the water phase by adding non-ionic detergent, okay, like adding some sort of a detergent or a surfactant, okay, which will try to flush it out, or we can even add organic solvents here actually. That is how you elute out. Okay. So, first is loading, then it is eluting out the protein. This is used in early stages of the separation process when protein is precipitated in the presence of salt. Okay. So, high salt concentration is ideal because you are achieving a salting out effect, and the proteins will have better interaction with the hydrophobic stationary phase. So, hydrophobic interaction, ion exchange chromatography, gel filtration are useful to remove protein without affecting the activity. So, basically you will get the activity of the protein back. We will talk about gel filtration later, but these three are very good because the activity of the protein is not lost. So, important parameters I need to consider: the type of ligand, percentage cover of the ligand in the matrix, composition of the matrix, type of salt used, salt concentration, pH, temperatures, any additives that are being used, and so on actually. Okay. So, we can also have different types of ligands attached on the chromatographic support. It could be alkyl groups of different chain lengths, like I can have a C8 group attached or a C18 group, so it will become very hydrophobic, or I can attach a phenyl group which is also hydrophobic. So, the former is very hydrophobic. The binding capacities of HIC matrices increases with increasing the hydrocarbon chain. Like I said, C8 versus C18, C18 will be very hydrophobic, whereas C8 relatively will be less hydrophobic. Common matrices used in HIC are 4 to 6% cross-linked agarose. They are strong hydrophilic carbohydrates. Smaller particle size leads to higher resolution, no? But then pressure drop also increases because pressure drop is inversely proportional to 1 by particle size square. Okay, so that problem you need to. Addition of salts leads to salting out, so increases the interaction between the protein and the immobilized ligand. So, I can have very high salt. So, concentration of salt, if it is increased, the amount of protein bound to the immobilized ligand also increases, that is the salting out. So, later on if I want to recover whatever has been bound, I will have a low salt, so that the bound protein will come back into the continuous phase. So, salts promote interaction and some promote elution of the protein. So, here the salting out effect which we talked about in the early class will come in the Hofmeister series. So, I can have different anions, cations as salt, okay, the increasing salting out effect, and this is increasing salting in effect. Okay, so, I will consider these salts if I am looking at the early initial stage of HIC, and I will use this type of salts if I want to recover the protein that is bound to the stationary phase, okay. And this is based on the Hofmeister series, okay. Changing pH improve interaction between the ligand and the matrix proteins. A ligand that do not bind to a hydrophobic interaction stationary phase at neutral pH may bind at acidic pH to it, okay. So, if it is not binding at neutral, then I may have to change the pH a little bit so that it binds at that pH actually. So, desorption of the protein bound, decreasing the concentration of salt, like it is almost like salting in, adding an organic solvent, adding a detergent, a neutral detergent or a surfactant. So, all these are tricks by which you can recover whatever has been bound, okay. Decreasing the concentration of the salt can be done in linear or stepwise fashion. Continuous gradients, salt concentration is decreased linearly and continuously. Step gradient, one or more salt solutions of a discrete concentration are passed through the column, okay. Stepwise is simpler, easy to perform, reproducible. So, water as an elutant also leads to desorption, that means water without any salt, right. Adding low concentration of water miscible alcohols, detergents help in salting in, like catatropic salts and so on. These all leads to desorption of the protein that is bound to the matrix. There is interaction chromatography. So, this is you are looking at a polar stationary phase, okay, then you are using a non-polar solvent, okay. Non-polar solvent, what is a non-polar solvent? It could be hexane, it could be toluene and so on. So, polar stationary phase, this is a normal chromatography. Whereas, if you look at the reverse phase chromatography, you have a non-polar stationary phase, that is the hydrophobic interaction chromatography, and you are having a polar solvent, okay, like water, that is a polar solvent, okay. So, here in a polar stationary phase hydrophobic proteins will come out first, whereas in a non-polar stationary phase hydrophilic proteins will come out first. So, interaction chromatography, polar stationary phase like silica gel and non-polar solvents like hexane, whereas reverse phase chromatography stationary phase is non-polar, elution phase is polar solvents like water. So, elution sequence for reverse phase, carboxylic acids, amines, sulfones, sulfoxides, alcohols, amines, esters and so on actually, and finally the alkenes are there actually. Surfactants are used because in the mobile phase, if you want to recover whatever has been, because surfactants have the ability to solubilize hydrophobic compounds, they selectively partition many solutes into micelles, it is cheap and it can also change the polarity of the mobile phase by adding that. So, what are the parameters? Column length, flow rate, temperature, solvent used, ion suppression. Sometimes if the protein has ionic groups, then it will appear like a polar. So, we need to suppress that, so that the hydrophobic part gets interacted with the stationary phase. So, we need to have some ion suppressing agents, sometimes you need to add ion pairing agent also, okay. Basically these are done to suppress the ionization of the protein. Higher molecular weight biomolecules can be purified on short column, increasing column length improve the resolution only marginally. Resolution of small peptides may improve by increasing column length. Resolution of large biomolecules is insensitive to flow rate. So, if you are doing flow rates with long columns, it may decrease resolution due to increased longitudinal diffusion as they travel longer. So, if I have a small column, you may get like this. If I have a large column, separation may be good, but it can go, peak may go very broad actually because of the longitudinal diffusion that is taking place, okay. So, we will continue in the next two classes more on the chromatography. Thank you very much.